Hi there. I bought this giant monster here because of its pretty spectacular specs, and it was not expensive because it's broken and was sold for parts. It's a Wayne Kerr auto-balancing universal bridge B642. This thing is basically an LCR meter, a bit like my Marconi TF2700, but quite a bit more advanced and possibly easier to use, judging from the manual. The right side is called C term and for capacitance and inductance, while the left side is called G term, which is the resistance and conductance part. So this instrument can measure resistance and reactance at the same time, which means it's really measuring impedance, and the autobalance in the name means it can be used to look at changing values. Here are the specs that convinced me to get it, even if it's just for looking and maybe harvesting parts. Capacitance from 1 femtofarad to 10 farads, inductance from 1 nanohenry to 10 megahenry, resistance from 10 microohm to 100 gigaohm. Wow, that is amazing. I've never seen any claims like that. By the way, the range with acute upside down omega is conductance G, which is the reciprocal of resistance. It was called mho, which is the reversal of ohm, but we call it nowadays Siemens. So 10 picosiemens is the same as 100 gigaohm, and 100 kilosiemens is the same as 10 microohms. Okay, the next part tones the specs down a bit. If you want 0.1% accuracy, the ranges are more like what you would expect. 1 picofarad to 10 microfarad, 1 millihenry to 10 kilohenry, 10 ohms to 100 megohm. But hey, 0.1% accuracy is actually quite a claim by itself and not to be sniffed at. Then we have a table with the actual range settings. This table presents what the unit will show you directly in the ranges from 4 to 10 with its G and C terms. This is actually for complex impedances with capacitance and resistance parts, but of course we can use it to measure just capacitors or resistors. The effect is that for a good capacitor the G term will be nearly zero, meaning very high parallel resistance, while for good resistors the C term will be near zero. The range for capacitance is from 10 microfarad down to 1 picofarad, and the first def column shows the resolution. So for example in the range 5 you could measure a capacitor between 100 nanofarad and 1 microfarad with 0.1 nanofarad resolution to 0.1% accuracy. Reciprocal values for G are 10 ohms to 100 megohm, and in the same range 5 the value could be between 100 ohms and 1 kiloohm. The fact that it reads conductance and one has to take the reciprocal to get ohms is easy today, but in days before electronic calculators, more of a headache, I imagine. Ranges 1 to 3 are for direct readout of more low impedances, but you can use it for measuring inductances from 1 microhenry to 1 millihenry or 10 milliohms to 10 ohms, but all only with 0.3% accuracy. Unsurprisingly, this range requires to use 4-wire connections because of the low ohms, and even then the manual explains that a correction factor has to be applied to account for the wiring of the bridge itself. The last table is the one that surely caused the most headache when this machine was used. The reason is that to measure these resistances and inductances you need to do more math. Resistance is straightforward, namely taking the reciprocal of the displayed conductance. For the inductance you have to use this formula to convert the C term. Omega is of course 2 times pi times frequency. Cunningly, the built-in generator uses 1591.5 Hz. That makes omega 10,000. So to convert, one has to take the measured C term, multiply it with 10,000 squared or 100 million, and then do the reciprocal. Of course, if you use external frequencies, then omega needs to be calculated for each case. The maintenance manual has a block schematic, and a lot of the secret sauce is in these complex transformers. On a high level, we have an oscillator on the left with a magic frequency of 1591.5 Hz to get a nice and easy omega of 10,000. That sine wave is used for measuring voltage and current through the unknown impedance. At the same time, the sine wave is formed into 2 square waves with 90-degree phase shift as references to the G and C detectors. I have seen more modern LCR meters to do away with the transformers, but kind of use the same principle and do the needed math for each readout in a processor. So much for the theory of that thing. Let's see what I received, and maybe it's even repairable. And we are off to a very bad start. The glass of the C meter has been pushed in and squashed the needle onto the scale. That meter with its -1 to +10 scale is not something found easily. The G meter at least is dirty but seems okay. The rear needs a clean, but it does not look too bad. There are two outputs to connect plotters for C and G, but can also be used to drive two DVMs. If these work, this is excellent news, because that means the broken C meter could be replaced by a DVM readout from this port. Apart from the DC output, we have a screwdriver operated switch to use internal or external frequency and some input BNCs. On the right is the voltage selector set to 200 to 250 volts, which is fine for the UK, a fuse and a very ancient 3-pin socket. This is the same as the one I found in the last video on the mystery high voltage box. Finding a matching plug or power cord will be tricky. The cover is held by these 4 spring-loaded latches that need just a half turn to disengage. Pulling the cover off reveals a solidly built inner chassis. Did I mention that this thing weighs a ton? The rear is held by 2 screws in the upper corners that are not the originals because they are the wrong size and very loose. The screws someone used here are metric, and this machine obviously uses imperial standards. The rear folds down, and I'm strongly reminded of old-style TV repairs by the dimensions and build. I also don't like the look of a half-empty PCB. The next revelation, there is no power supply, just a cut cable where the power supply used to be. Another look at the insides of the machine. It is hard to convey how big this thing is and how much space it takes on the bench. A bit of good news, I checked the service manual and it appears that the empty spaces on the PCB are normal, so at least on first glance nothing was removed. The same cannot be said for the power supply, which is AWOL. It should be on the rear panel right above the power inlet, but only the hex standoffs are left. So much for me worrying about a matching power cord. It appears instead of a power supply, the previous owners added some terminal blocks, probably to keep the now orphaned power supply wiring tidy. That loose cable is in fact connected to one of the terminal blocks, so it's something that the previous owner added, not something left over from the original. The power inlet connector still has its ground and live wires attached, but neutral has been cut off. 2 caps provide some filtering. Testing the conductivity of the black ground wire of the power inlet connector reveals that it's connected to all the black wires on the 2 terminal blocks. I summarize the testing of the conductivity of the red live wire. It is connected to the fuse and from the fuse to the voltage selector, and it ends there. It is not connected to anything in the terminal blocks, even though it uses exactly the same thin red wire that is used there. Also not shown, the red live wire from the power inlet goes first to the on-off switch on the front and then to the fuse. A safer way would be doing it the other way around. Anyway, as this is all that's left of the mains wiring, it means the terminal block wiring must be outputs from the now missing power supply. This is confirmed in that the red wires in one of the terminal blocks are connected to the +9 volt input of the PCB. And the purple wire in the same terminal block is connected to the -6 volt input on another PCB. This leaves the question where the red wires of the second terminal block go, and I suspected the indicator lamps. There are 9 indicator lamps in this meter, and the easiest accessible ones are the ones for the sensitivity switch in the middle. With one probe connected to the terminal block, I check conductivity. And yes, this is the +200 volt input for the neons. Now that I understand what power goes where, I could try powering this externally, but before that the broken C meter has to be fixed or at least disconnected. I struggled for some time because the area is so packed that it's hard to get a proper grip on the ring securing the meter. At the end I did manage without breaking anything, including my fingers. Off camera I got the glass out and bent the needle back, so it doesn't drag over the scale anymore. And amazingly, the meter still works pretty well. I tried to open it to glue the glass back on, but so far I have not found a way to open it non-destructively. I connected a 200 volt power supply temporarily to the second terminal block, and turning just the 200 volts on, nothing else, the lights come on. The upper ones indicate the sensitivity of the bridge. Maybe one can live without these working. The lower ones are driven by the range switch and indicate where the decimal point of the readout is. These patterns look pretty complex. Without working lights, one would need to always reference a lookup table. So if I get this bridge working, making the lights work too is probably worth doing. I attached 9 volts for my bench power supply, which should be enough to get the sine generator working. It's an oscillator known as a Wayne bridge. There's an exhaustive article about it in Wikipedia, and I refer you to it. Sadly, I could not detect any type of sine wave signal coming out of this circuit. By the way, in case you wonder, that thing that looks like a small tube or valve is in fact a special thermistor, similar to a light bulb to stabilize the oscillator output. The circuit diagram of the oscillator. Of note is that this circuit works either as an oscillator when the int X switch on the rear is set to int, or as a buffer amplifier for an external frequency input when set to X. So a problem in that switch or wiring could be the reason for not seeing any oscillations. A closer inspection of the int X switch and associated wiring, and indeed one of the tabs had broken off at a switch. I managed to solder the tab back on. The failure mode of this tab is quite obvious. Originally the cable must have been sticking out slightly, forcing the tab to bend every time the rear panel was closed or opened until the tab finally broke. Sadly, that broken tab did not fix the oscillator, but by chance I noticed that one of the transistors was wobbly. All transistors are mounted on some black holder, so you can't see the legs, but it feels as one of the legs of the VT26 is broken. There was no indication of anything wrong on the underside of the PCB, and they folded the legs, making it quite hard to desolder. But one of the legs had definitely broken earlier before my desoldering. The transistor itself, a BC109, tested okay. I debated putting it back in without a black disc as the legs were too short, but in the end I decided to replace it with a new BC107B for my parts bin, but still decided not to use that black holder disc. And yay, the first sign of life in this old machine, the oscillator's working. But not quite at the right frequency. It should be 1591.5 Hz, but it's only 1578 Hz. I worry about that later. To test more, I need to be able to power this thing while the rear is folded up to have more space on the bench. So I probably added what the previous owner did, namely an extension to connect the plus 9 volts and minus 6 volts from the outside. Optimistically, I connected a test resistor via BNC to alligator clips to be measured, but not much is happening. At least I can see there's a signal on the resistor and it's changing with range, so that's encouraging, but nothing of the rest works. I did not connect the 200 volts, so that's why there are no lights. Driving this thing from 2 external power supplies is already complex enough. So the oscillator signal is at the test object, and then it gets lost apparently. If you remember from before, the signal from the probe has to go through a feedback amplifier before it reaches the phase sensitive detector and instruments. So I traced the signal and I did video that, but I seem to have somehow lost those files, sorry. I could see the signal in the scope getting into VT8, but nothing came out on VT12. It was still at C17. Measuring diode junctions across transistors quickly narrowed the problem down to VT29, another BC109. I desoldered it, and it was another case of broken pin, with the transistor actually fine. I replaced it with another BC107B, and now the signal got through. Here's an image of the board after I fixed it. VT29 is the new transistor without that silly black disc. I wonder if these mounts are actually stressing the legs somehow. Anyway, with that the G meter showed some movement, but not the C meter. The phase sensitivity detector is the board left from the Wayne oscillator. It drives the meters and also contains the square wave reference generators. I can see a nice square wave on the square wave generator of the G term, but nothing on the one for the C term. Clearly there's something wrong on this board too. The circuit diagram shows that the G and C parts are nearly identical, which is very nice because it allows me to compare measurements between the G part that works, at least to some extent, and the C part which doesn't. Sadly, I came to the conclusion that the amplifier chip for the C term was defect. That chip, an SL702C, is a strange beast, not your standard op amp, and certainly very vintage. Luckily, I was able to find it on eBay as new old stock. I had to buy 2 for a total of £9, but okay, at least I got a spare. Okay, compared to the G-term chip, my replacement install looks decidedly sloppy, but I just wanted to see if it works and tidy later. It's a strange way of installing, having it floating on pins, but at least I could do it all from the top without having to disconnect everything to remove the board. And it works very well. A beautiful square wave now on the C term as well. I was a bit worried because with eBay chips, especially with new old stock, you never know. But it looks similar in amplitude and shape as the one from the original chip for the G term. And now at last I can actually follow the setup procedure in the manual that one has to do at the beginning of using the bridge. I even rigged up a third power supply for the 200-volt light circuit for this occasion. With the range set to 4, I turn the sensitivity to 3, which is the highest setting. Then use the trim knobs for C and G to zero both meters. First a C term and then the G term. The two may slightly influence each other, but it seems to work just fine. Then I set the sensitivity to calibrate and adjust the C meter to full scale, that is 10, using the FSD knob, and adjust the G meter to 0 using the 0 knob. Again, the two adjustments slightly influence each other and you may have to repeat these steps. There, now the sensitivity switch to auto and the instrument is ready. Connecting a 100 nanofarad capacitor that I previously measured to be just over 90 nanofarads, and now I'm supposed to increase the range until either meter shows more than 1. The C meter wins, showing 9. The next step is to set each of the first knobs of each decade control to the corresponding value the meter shows. For G that is 0 because it's less than 1, and for C that is 9. Now the meter shows the second digit and sensitivity has increased automatically to 2. If more accuracy is needed, repeat the step. Set the next digit on the G term to 0 as well, and the next digit on the C term to 1, and the sensitivity is now automatically increased to 3. The meters show now the third digits, and so on. You get the idea. One can stop at any time if the needed accuracy is reached. We have a G term of 004.5 microsiemens, equivalent to 222 kiloohms, and a C term of 91.6 nanofarad. Excellent. This bridge is back in business. In playing some more, I discovered some more faults, courtesy of the previous owner. The decade knobs are not identical, and some in the C term are obviously wrong. Like the one on the most left in this picture, which is actually the second digit. Clearly, there are no markings behind the -1, even though this rotary switch has more positions. The most right knob controls actually a potentiometer, not a rotary switch, and that has only a 270-degree range. So these two knobs have been accidentally swapped, and I need to undo this by taking the cap off, losing the nuts until the knobs can be pulled off, swapped, and then tightening everything again without losing the red 0 position, which is essential for the working of the bridge. So the second decade now has a digit readout for every switch position. and the knob for the potentiometer now doesn't have a digit readout for position that can't be reached. But then I noticed that the most left knob, remember that's the second decade switch because there is one more to the left, should really have a 10 position, at least the procedure in the operator manual assumes that it has. So the left and middle knob here have to be swapped too. While the maintenance manual warns that the knobs for the decades are not interchangeable, they did not bother to print a little reference that tells you which knobs goes where. I bet that accidentally swapping knobs producing wrong readouts was a common problem with these bridges. At least the G term seems to be okay, and now the C term knobs match the order of the G term. As I mentioned before, this bridge has DC outputs for the meter readings. These need to be calibrated so that when the meter shows 10, you get 1 volt. To do that, I need to remove the protective caps of the trim pods and, of course, connect the DVM. That was no issue for the C term output, but I was not able to plug anything into the G term output. On closer inspection, the reason why nothing can be plugged in is a broken off piece of banana plug stuck in the socket. This bridge really must have had a hard life considering all the problems I've found so far. That stuck plug could have been an issue forcing me to replace the socket, but it turned out because the broken plug was a hollow type, it was easy to grip and pull out. We have come a long way. The next thing is obviously to replace the missing power supply, adjust the oscillator and maybe play some more with the bridge, but that will be in the next part. If you like my videos, don't forget to subscribe. There are many more projects, repairs and reviews coming up, and it would be great if you decided becoming a Patreon. That would really help this channel. Thanks for watching.